Welcome back to our biomass class, where we're delving deeper into the fascinating world of conversion of biomass resources into heat and power. This video was made with the support of Energy. Remember that this biomass energy course has 9 lessons. Lesson 6 has an introduction and several videos that go deeper in some applications of biomass gasification. In this video, we analyze the application of biomass gasification technologies. Let's start by analyzing what differentiates gasification from other thermochemical processes, especially with regard to flexibility. Gasification takes place when there is not enough oxygen to have a complete oxidation. In that case, the products are synthesis gas and ash. The conversion of a solid fuel into a gaseous fuel provides flexibility. The syngas can be used in a gas turbine, in an internal combustion engine, to produce chemicals, and so on. The question is, why do we need flexibility? And what advantages can offer gasification when compared with conventional processes for power generation like combustion with steam cycle? Let's imagine that your company wants to build a new biomass-fueled power plant. The first thing to analyze is the sustainable production of forest biomass in the region. We can consider an average heating value for the biomass produced. Finally, the electrical power to be produced, and a rough estimation of the efficiency in the conversion of the biomass energy into electricity. With a simple formula, we can calculate the radius of influence of this power plant. Taking into account that the cost of transportation increases with the distance, it is easy to imagine that the higher the radius, the lower the economic feasibility of this power plant. In Northern Europe, this cannot be a problem. However, will it be feasible in the Mediterranean area to install a big power plant? The answer will be that probably not. Does this mean that biomass power plants are not feasible? What about using other feedstocks, like residual biomass and refuse-derived fuel from municipal solid waste? Using blends of low-cost fuels allows to design plants with higher power capacity and higher energy efficiency, keeping low prices for the feedstock. All this increasing the economic feasibility of the project. In this scenario, gasification can offer solutions: more flexible, more efficient, with lower environmental impacts, and with higher simplicity than pyrolysis processes. Because its flexibility, gasification offers a wide set of technical solutions for power generation. One simple solution is co-firing the synthesis gas with coal. This solution was adopted in late 90s in the Kimijärvi power plant in Finland. In 2012, the old biomass gasifier was substituted by a waste gasifier. This solution has the advantage that does not need gas cleaning and conditioning. Gasification with steam cycle is also commercially available. Several plants operating with circulating fluidized beds have been constructed in Europe by TPS and Lurgy. In that case, the syngas is burned in a boiler that produces steam. The steam is sent to a turbine for producing electricity. In that case, gas cleaning requirements are now so high. Gasification with internal combustion engine. For using the syngas in an internal combustion engine, it must be cleaned and cooled. The content of particles, tars, and alkali metals must be under specific limits to guarantee a good performance of the engine and to reduce maintenance problems. There are some pilot units, in general, below 1 megawatt of electrical power. Some small-scale solutions are already available for powers below 500 kilowatt. Usually, they operate producing combined heat and power. BICGT is biomass internal combustion gas turbine. In that case, the syngas is sent to a gas turbine, which is coupled to an electricity generator. Like for an ICE, particles, tars, and alkali metals must be removed. However, in this case, the limits are far below than for an engine. These processes have higher biomass to electricity conversion ratios. However, they still need to solve operational problems and achieve lower investment costs. When the hot flue gas from the gas turbine are used to produce steam, and this steam to produce more electricity, we have a combined cycle. Known as BIGCC, it is a complex process. This is the process with the highest biomass to electricity conversion ratio. Several pilot plants have been constructed in the past in USA, UK, Italy, and Sweden. Most of these plants have been shut down. BIGCC still need to solve operational problems and achieve lower investment costs. At present, its economic viability for biomass is in question. Small-scale CHP systems. Some studies demonstrate that for electrical powers below 1 megawatt, the most feasible solution is gasification with internal combustion engine operating under the CHP concept. That is, generating both heat and electricity simultaneously. These systems are already commercially available and usually include a downdraft gasifier. Biomass to electricity conversion is not very high, maybe around 25%. However, these systems can provide 2 kWh of heat for each kilowatt-hour of electricity. This rises the overall energy efficiency above 70%. Wrapping up. For power generation, biomass gasification can offer some advantages when compared with combustion with steam cycle. Thanks to its flexibility in the feedstock, gasifiers can operate with a mixture of different types of biomass and residues. This can improve their economic feasibility. When integrated in combined cycle, the electrical efficiency is higher than for conventional combustion processes. However, BIGCC are still in the demonstration stage. Because its flexibility, gasification allows also other configurations. Gasification with steam cycle or co-combustion of the syngas are commercially available technologies. Also in the commercial stage, we can find small-scale gasifiers operating in CHP systems.